Alright, so today we want to start talking about kinematics in more than one dimension. But before we do that, let's review briefly the basic ideas of kinematics in one dimension. So, actually I guess that's fine. Remember that we had a position vector based on an origin, which would run from the origin to the position we were considering. At a later time, we could have a different position vector, which ran from the origin to the position. And then the difference between those two, the change in position, was known as the displacement vector. That's r2 minus r1. And in one dimension, I could just subtract numbers. Now, a couple of things to remember. Remember, the position vectors depended on the location of our origin, whereas the displacement vector was independent of our origin. A couple other things. Distance was a scalar. It was the total path length between the beginning and final positions, and it was not the same in magnitude as the displacement. Average velocity was the rate of change of displacement, so it was delta r, the displacement, over the change in time. In one dimension, it was just delta x over delta t. And speed was a scalar that was related. In speed, we took the distance divided by the change in time. Then if we wanted to do those instantaneously, we couldn't simply say that the change in time was 0, because then we would have 0 on the bottom of our denominator. Instead, we took a limit as the change in time went to 0, as the change in time became very small. And we got the derivative, dr dt, or in one dimension, dx dt. So that was the derivative of position with respect to time that became the velocity. It turns out that because over a very short distance you can only travel in one time, in one direction, the distance over the change in time in that same limit is just the absolute value of the speed. Excuse me, the absolute value of the velocity. So speed is the absolute value of velocity in the instantaneous case. In the average case, not necessarily. Then when we got to acceleration, acceleration was how quickly the velocity was changing. So the average acceleration was the change in velocity over change in time. And then if I wanted an instantaneous acceleration, I simply took the limit as delta time went to 0, and it became a derivative of velocity with respect to time. And in one dimension, that was just the derivative of Vx with respect to time. And we came up with these very useful equations. The two here on the top are our main equations. Change in position is the initial velocity times the time, plus 1/2 the acceleration times the time squared. And final velocity is the initial velocity plus the acceleration times the time. This one down here we kind of alluded to in one problem that we worked. You get it by solving this equation for time and plugging it in here. There are a number of other equations that can be useful. So you might remember the delta x was 1/2 v initial plus v final times t. This one you can get by solving this one for time and plugging it in here. Excuse me, no. That one you get by solving this one for acceleration and plugging it in here. And there's also one where if you solved this one for initial velocity and plugged it in here to get final velocity, you could say delta x is equal to v final x t minus 1/2 a t squared. These ones here are all sort of secondary equations. The top two are our primary equations that we want to work with most often. These last three can all be derived from the top two.